Hello. Today, in this video lecture, we will move towards this part B of this chapter, axially and eccentrically loaded chapter. And this part B is direct and bending stresses for eccentrically loaded short columns. So, first see direct load. The load which is coincide with the centroidal axis of the column. This P is load and it is coincide with centroidal axis of this column is called as direct load. And it produces direct stress only. So first break down this definition. The load which is coincide with the centroidal axis. So first understand what is centroidal axis. Centroidal axis is nothing but the see this shape. This is rectangular shape. So that rectangular shape I have drawn here and see centroid. This C is centroid of this rectangle. Let me and this is x-axis, this is y-axis. Let us consider this x-axis and y-axis of this rectangle, and this side is A side, this side is B side. So this C is y bar distance from that x-axis, and this C is x bar distance from that x-axis. So first understand that centroidal, like centroid of area. So this centroid of area, that means centroid of that figure is defined as the point at which the whole area of the lamina or figure may be assumed to be concentrated. So in this point, whole area or lamina of the figure assumed to be concentrated. So this x bar, see this x bar is nothing but the, see this side is B, this is x bar is nothing but the B by 2, and this is y bar is nothing but the, this side is A, see this is A by 2. So this is x bar and y bar. And area of this rectangle, you know that area is nothing but the, this is A side B. So let us denote area as capital A. So this area A into B. So this is centroidal axis at which whole area of the, that means this is centroid of area. So understand that definition. Centroid, what is centroid? Centroid of plane lamina or figure is defined as the point at which whole area of the lamina or figure may be assumed to be concentrated. And centroidal axis is nothing but this, that axis go through that centroid. This is x-axis, x-axis centroid axis. This is y-y centroidal axis. So this is the definition of that. Then the load at which coincide with the centroidal axis. That means here at C point, C, this load P, this is coincide with the centroidal axis is called as direct load. And it produces direct stress only. So who produces direct stress? Direct load produces direct stress. This P is nothing but the direct load, and this sigma is nothing but the direct stress. And this area is area. So understand that also what is direct stress. See here, I have written here that stress, the internal resistance, set up per unit cross sectional area. So this internal resistance and cross sectional area. Internal resistance set up per unit cross sectional area is called as stress or intensity, or yes, intensity of stress or unit stress. And this is also denoted as sigma. Sigma is equal to R by A. This R is nothing but the, that internal resistance, and A is area. So see, in the equilibrium condition, the internal resistance R is equal to an external load P. See, if it is column like that, and this load is acting on centroid of this. So Due to that action, there is equal and opposite reaction. Like here, equal and opposite reaction occurs. That's why this P is equal to R. So due to that react load in the equilibrium condition, the internal resistance R equals to an external load. So sigma is equal to R by A is equal to P by A. So stress, sigma is stress, P is load acting on the body, area is cross sectional area of the body. So see this one definition. Let us assume that as a RCC column, and that RCC column, RCC beam. Let us assume this as RCC beam, and that beam that P tensile loads acts on it. So due to that tensile load, there is resistance force develop inside that beam like that. See, I have break here in that X section that beam, and this is this part of the LHS part of that beam and RHS part of that beam. So this is that LHS part and this is RHS part. So these forces are nothing but the resistance force when we apply any load to that beam. And here we had applied tensile load. So due to that tensile load, that beam resists that forces. So see here, sigma is equal to P by A. So 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 learn this formula. If we will increase that area of that beam, then that stress will be decreased. So if load increases, stress increases. So remember that relation between that sigma is directly proportional to P. Load is stress is directly proportional to load, and stress is inversely proportional to area. So remember that. Inversely proportional, that means there is reverse relation. If stress increases, area decreases, like that relation. And directly proportional, that means that stress also increases, load also increases. Stress decreases, load decreases, like that type of relation they have. So this stress is nothing but the internal developing that force upon area. So due to that load, that there internally develop that stress. So remember that. Remember this word, internal resistance. The internal resistance set up per unit cross sectional area. So so stress is nothing but the resistance for that force. Remember that. Eccentricity. Now see this eccentricity. What is eccentricity? It is horizontal distance between the line of action of force and centroidal axis. So what is this line of action of force? Line of action of force, that means see this is rectangular column, elevation of this column, and but one difference in that section, that in that elevation, is that load is shift away from that centroidal axis. So that load is e distance shift away from that centroidal axis. See this e and this p, and this line of action is nothing but this line of action of force. That means see this load, how is load acting like that way, and that this is line of action of force. If load is acting like that way, that means this is line of action of is like that way, this is line of action of force. So that is line of action of force. And the centroidal, and distance between that line of action of force and centroidal axis. Centroidal axis, that means here centroid of that. So distance between that is e, and e is nothing but the eccentricity. It is denoted as small e, and it produces bending stresses in the member. See, if my member is this, and if some eccentric load is acting on that beam, then this uh, will buckle like this. So due to that it produces buckling. And see this bending formula. Bending formula is m by I is equal to sigma by y is equal to E by R. M is nothing but the bending moment. I is nothing but the moment of inertia. Sigma is nothing but the bending stress. Y is that distance between elemental strip and that neutral axis distance. E is nothing but the modulus of elasticity, and that R is radius of that curve portion, because this is bending stress. So now see this m by I is equal to sigma by y. So rearrange it mathematically. This, then this, then this sigma is equal to my by I. Then this y take this bottom side, m by I by y. So sigma is equal to m by z. M is nothing but the moment and z is sectional modulus. So I will tell you what is sectional modulus. This y is nothing but the distance between centroidal axis and that elementary strip distance. We had seen it in our that second chapter, bending and shear stresses. Now see this z. What is this z? Sectional modulus. Sectional modulus or modulus of section. It is nothing but the see sectional modulus of section. This is z is equal to I by y. That means this is nothing but the moment of inertia about any axis, either this y by axis, either this x axis, and distance between that either x either y moment of inertia and that extreme fiber distance. That means this is nothing but y, and this y is this y, and moment of inertia is either this y either this x. So that is sectional modulus. See definition. Sectional modulus is the ratio of moment of inertia of any section about its neutral axis. Ratio of moment of neutral axis, that means either y axis either x axis, to the distance of extreme fiber from the neutral axis. It is denoted by z and unit is meter cube, because see this is mm raised to 4 and this is mm, so that's why mm cube. So now see this eccentric loading. This eccentric loading is nothing but the load which the load whose line of action does not coincide with the axis of column is called as an eccentric loading. So like that way, see here, load isn't coincide with this line of action. This is load. This isn't coincide with that centroidal axis. So between load and that centroidal axis, there is some e distance between both of them, and it produces buckling in the column. So see here, this is e distance. So this is a rectangular shape column. Let us assume that at fixed at bottom, and this load is acting like that way. This is P load is acting like that way, and here this is centroid of this column, centroidal axis. So due to that, see what is happening. Due to that P load, here some axial load comes and also movement is also come. So that's why here this B is axial load and this C is movement. Due to that P, that both are coming. This B and C are coming because of that eccentric load P. Due to eccentric load, both direct stress and bending stress induced. And see, we had seen that combined maximum stress is nothing but the direct stress plus minus bending stress. So the sigma is combined maximum sigma is stress is equal to direct stress plus minus bending stress. Direct stress is nothing but the P by A and bending stress is M by Z. So maximum stress sigma max is equal to P by A plus M by Z. And remember that here plus sign, this is compressive for that maximum stress, and minimum stress sigma minimum P by A minus M by Z. Remember that this minus cell and this tensile. So this is that introduction of that B part of that chapter, eccentrically loaded columns. So again see that so direct load is nothing but the load which is coincide with the centroidal axis of column. And what is centroidal axis of column? That axis which are passing through centroid of that column. Centroid is this C. And what is this centroid? Centroid of area, that means at which whole area of the lamina or figure is to be concentrated. That direct stress is nothing but the P by A. This is direct stress. And direct stress and bend, see difference between both of them. Direct stress and bending stress are different. Bending stress comes due to bending in member, and direct stress comes due to that tensile compressive forces in member. So see, if force is acting, that is not the case. If that is not the case, if it is acting like that, then in that RCC beam that bending stress will develop. Now it is that in longitudinal line, tensile in compressive. So that's why that this stress is developed, that V stress, direct stress. Difference direct stress and bending stress. Learn different. So eccentricity. What is eccentricity? Horizontal distance between line of action of force and that centroidal axis for that rectangular column. That sectional modulus I by Y. Sectional modulus is the ratio of moment of inertia of any section about its neutral axis to the distance of extreme fiber from the neutral axis. Eccentric loading, that it produce buckling in column. That is very important statement, that eccentric loading produce buckling in column. So maybe because of that movement P into E, these are developing buckling in that column. So that combined maximum stress is P by A plus M by Z, and it is compressive. Plus sign comes, that's why it is compressive. And if minus sign comes, that means it is tensile. Remember that. So that way our introduction completes. Thank you very much.